For nearly 50 years, they've been venturing through the vast reaches of space, delivering groundbreaking discoveries from regions of the cosmos once beyond our reach. The legendary Voyager probes, long known for crossing the outer limits of our solar system, have brought back more than just insights from interstellar space. In fact, not all transmissions making their way back to Earth have been expected, or even explainable. Some time ago, Voyager 1 began sending back a stream of strange, chaotic data, sparking concern and intrigue among NASA scientists. The information was so unusual, it was quickly labeled as abnormal. But what exactly triggered this unexpected behavior? Did Voyager 1 encounter something so bizarre that it disrupted its systems? Or is this a case of even the toughest machines finally beginning to fail after decades in the void? Stick with us until the end as we uncover the truth behind this extraordinary event. It all began with a bold idea. Today, the James Webb Space Telescope peers deeper into the ancient secrets of the cosmos than ever before, but back in the 1960s, things looked very different. At that time, a mission to the outer reaches of the solar system seemed nearly impossible. The reason was simple: Jupiter, Saturn, and the other outer planets are so far away that any space probe would require more fuel than a rocket could possibly carry. The thought of studying all four of the solar system's outer planets up close felt like pure science fiction, until a man named Gary Flandreau entered the picture. Assigned to find a way to make such a journey more efficient, the young doctoral student working at NASA's Jet Propulsion Laboratory in Pasadena recalled an intriguing astronomical phenomenon. When Uranus approaches Neptune, it appears to accelerate briefly before slowing down again, a behavior that had also been noted in comets. This observation would lay the foundation for something extraordinary. Could space probes harness the gravitational pull of planets to boost their speed? This idea deeply intrigued Flandreau. After thorough analysis, he concluded that not only was it possible, but a probe could use multiple close flybys and planetary orbits to gain momentum and visit all the outer planets in a single mission. This approach could potentially cut the travel time by nearly 20 years. However, this concept relied heavily on a rare and favorable alignment of planets. As fortune would have it, Flandreau discovered that such a unique planetary configuration would occur in the mid-1980s, when all four gas giants, along with Pluto, would be positioned on the same side of the Sun and relatively close together. This rare alignment happens only once every 175 years. Thus began the conception of the Voyager mission. With the clock ticking, NASA quickly moved to design and develop a mission plan. Had everything gone as originally planned, four space probes, not just two, would have been launched in 1977 to explore the outer planets, which remained mostly uncharted territory at the time. However, the $900 million price tag proved too steep for the U.S. government. With the moon landing already securing victory in the space race, space exploration had slipped down the list of budget priorities. As a result, the program was scaled back to just two probes, and the mission plan was stripped down to its essentials. The revised goal: visit Jupiter, Saturn, and Saturn's moon Titan. The extended journey to Uranus and Neptune was shelved for the time being. It's impossible to know how NASA or the government would have responded had they known the Voyager probes would one day leave the solar system and enter interstellar space. What is certain, though, is that the spacecraft had to be built to endure a long voyage. Modeled after the Mariner probes, Voyager 1 and 2 were engineered for a mission lifespan of up to 10 years, a duration that seemed unimaginably long back then, especially given the intense radiation they would face near Jupiter. All critical components were equipped with special protective shielding. At the same time, essential systems, such as the onboard computers, data storage units, and radio transmitters and receivers, were installed in duplicate. By today's standards, the technology used may seem almost laughable. After all, the computing power of the Voyager probes is barely more advanced than the automatic door opener of a modern car. To put it in perspective, Voyager's onboard computers can handle around 80,000 instructions per second. By comparison, even an outdated smartphone collecting dust on your shelf can process over 15 billion instructions per second. Yet, While our old phones can't venture into deep space or redefine our understanding of the cosmos, the Voyager probe certainly could. That journey began on August 20, 1977, but surprisingly, it wasn't Voyager 1 that launched first. Voyager 2 lifted off from Cape Canaveral, Florida, with its identical twin following on September 5. Due to its shorter trajectory toward Jupiter and Saturn, Voyager 1 was still expected to reach its targets first, living up to its name. Indeed, Voyager 1 entered the Jupiter system in March 1979, sending back breathtaking images of the gas giant. These included visuals of its turbulent atmosphere and, for the first time, lightning strikes observed on another planet. Even more remarkable was the discovery involving Jupiter's innermost moon, Io. Previously assumed to be a frozen and inactive world, Voyager's data revealed it to be unexpectedly vibrant and geologically dynamic. And with good reason. Later analyses confirmed that Io is an incredibly active volcanic moon. The flybys of Europa were equally remarkable. Stunning images of its icy crust, along with data on its density and thermal activity, offered the first hints that a vast ocean of liquid water might lie beneath its surface. Even today, Europa remains a prime candidate in the search for extraterrestrial life. A close pass by Titan, just 6,500 kilometers away, revealed a nitrogen-rich atmosphere laced with hydrocarbons. At the time, it was only likely that the methane and ethane on its surface were in liquid form. Now, that assumption has been confirmed. Titan is home to actual lakes and rivers of methane. Voyager 2 then treated us to awe-inspiring views of the Saturn system. Alongside the stunning visuals of Saturn's rings and its many moons, something unexpected occurred, something that, in hindsight, felt like a troubling omen. A major technical issue threatened to derail the entire mission. After gaining speed at Saturn for its journey toward Uranus and Neptune, Voyager 2's camera suddenly jammed. Thankfully, the problem was eventually resolved. What exactly happened during that time still remains a mystery. However, it's no secret that Voyager 2 reached Uranus in January 1986. During its visit, the probe made remarkable discoveries, identifying 11 previously unknown moons and revealing that Uranus, often classified as a gas giant, is actually more accurately described as an ice giant. Beneath its gaseous outer layer lies a dense shell of water ice. But that wasn't the only surprise. Uranus's magnetic field is truly unusual, featuring 4 poles and a distorted, corkscrew-like structure. Equally puzzling were the strange readings from Voyager 1 regarding Uranus's moon Miranda. Its extremely rugged and mosaic-like surface left scientists baffled, as no other celestial body exhibits such peculiar terrain, and we still don't fully understand why. In contrast, our picture of Neptune became much clearer after Voyager 2 flew by in August 1989. Like Uranus, Neptune turned out to be an ice giant with an equally strange magnetic field. What followed for Voyager 2 was a voyage into uncharted space. Voyager 1, however, had already departed for the outer reaches of the solar system back in 1980. It made history on August 25, 2012, by becoming the first human-made object to enter interstellar space. Voyager 2 joined it there in November 2018. The Voyager probes revealed that the region beyond our solar system is far more intricate and dynamic than once believed. Contrary to the idea of deep space being empty, it's actually filled with the interstellar medium, a mixture of gas, dust, and cosmic radiation. This medium has a significantly greater impact on our heliosphere, the protective bubble surrounding the Sun, than previously assumed. In fact, it exerts up to 10 times more pressure on the heliosphere and engages in more interactions with it than earlier models suggested. One key discovery near the heliopause, the outer boundary of the heliosphere, is a powerful magnetic barrier. This barrier serves as an extra shield, helping to block incoming cosmic radiation. The data gathered by the Voyager missions has been both groundbreaking and exclusive, offering rare insights into interstellar space.